the improper integral of x cubed from minus infinity to infinity, and you should have computed that the integral does not converge. So you can also see that by thinking about the graph of x cubed, and you can see there's not a finite amount of signed area under the curve here. I just want to point out that it's kind of tempting to want to take fewer limits in this situation and just fix one number b and then try to consider the integral from minus b to b. And in that case, right, you actually don't get the answer that we're looking for here. So if you think about the limit as b goes to infinity of the integral from minus b to b, x cubed dx, right? X cubed is an odd function, so this area for any b is equal, the signed area is equal to 0, and so the limit therefore as b goes to infinity is also 0, and this is not equal to the improper integral that we're interested in. So this is not this is not the right picture here. So let me go ahead and just cross it out. You don't want to do this. Instead, what you want to do is two separate limits. Okay, I would like to conclude with one more example of the improper integral from minus 1 to 1 of 1 over x squared dx. And so you've already seen this integrand several times before. And so let me just re-sketch very quickly a little cartoon here for us. We have a vertical asymptote right at 0, and we want to integrate from minus 1 to 1. And so in this cartoon here, what we would need to do is consider limits. So let me I'll switch colors real quick here. We would need to consider a limit as we let c approach 0 from the right. And if we didn't know that this function was symmetric, we would need to then take a separate limit, take another point here in this other interval and then consider another limit. However, we know that 1 over x squared is symmetric, so we can just write the integral from minus 1 to 1 of 1 over x squared as 2 times the integral from 0 to 1 of 1 over x squared dx. And in this case, now we can write this with a limit. And then we can use the power rule to evaluate this limit. So 1 over x squared is x to the minus 2. So we have x to the minus 1 over 1 evaluated at c and 1. And notice at each step along the way, I'm writing the limit. Since we have not yet evaluated the limit, it needs to be included in every expression in the calculation. oops, this should be x to the minus 1 over minus 1 here. And so when I plug in 1, we're going to have negative 1, and then we'll get plus 1 over c. And now, if you think about it, as c approaches 0 from the positive side, 1 over c is approaching infinity. So this is approaches infinity. So this does not converge. Sometimes people use the shorthand notation and just write that this equals infinity in the sense, okay, it doesn't converge, and it's this limit is a positive number that grows without bound. In any case, there's another way of saying that is there's an infinite amount of area under this curve here. So we have divergence for this particular integral. And I think it's kind of interesting to compare several of these functions that we've been looking at. And so let's just go to Desmos quickly and do that. In particular, let me actually, before we go to Desmos, let me just summarize a couple of the interesting things that we've seen. So when we think about the function integral from minus, and in fact, let me just even not think about minus 1 to 1. Let's go, from, okay, this auto fill in is not doing what I'd like it to. Okay, so if you recall, we had the integral from 1 to infinity of 1 over x squared dx did converge, right? So this we computed way up here, and we found that this integral was equal to 1. That was our very first example. And so we found that this equals 1. On the other hand, we found that the integral from 0 to 1 of 1 over x squared dx doesn't exist. So sometimes I abbreviate converge as CGE. Okay, so let's take a look. We also saw that the integral of 1 over x to the 1.5 dx from 1 to infinity converges, and I believe that was equal to 2, if I'm remembering correctly. Right, so that was 2. Sorry for the fast scrolling here. Right, so this did converge as well, but we saw that the integral from 1 to infinity of 1 over x dx did not converge. And so I just wanted to go to Desmos and compare a few of these functions so you could kind of see what's happening here. So let's go and do that. And so let's go over here to the graphing calculator, and let's define a bunch of functions here. Let's define f of x equals 1 over x. That will be the first one. We'll do another one, g of x equals 1 over squared. And let's add a third one, h of x equals, equals 1 over x to the 1.5. All right, so now let's zoom in and take a look here. So we have if we're looking from the blue is 1 over x squared, that's the lowest, and the area from 1 to infinity we found was 1. The green is the next highest. If you're just restricting your attention from 1 to infinity, the green is always above the blue, and so you can see there's more area there, and in fact the green area was 2. So that's kind of interesting that we can even say how much more that is. It doesn't look like an area of 2 to me, but in fact if you added all of this all the way out, you would have exactly twice as much under the green curve as the blue curve. And then if you look at the red curve, that's 1 over x. And 1 over x, in fact, is above the green curve. And it turns out that 1 over x has so you can see that it should have even more area than the green curve, but it actually has an infinite amount of area. So I'm going to go ahead and just add one more of these, and we're going to call it k. K of x equals, and now we'll just say 1 over x to the, and I'm going to put in p here. Now, Desmos does this really cool thing. It adds a slider if you click add slider here. And now, okay, it's starting out as 1 over x here for k of x, but then I can add a slider and I can see what happens as I vary p, and you can see here this purple now is at p equals 5, and for p equals 5, that's 1 over x to the 5th, and you can see that this curve is much further below 1 over x squared, the blue curve there. So you could make a conjecture about whether or not there's a finite amount of area there. Let me go ahead and scroll over. And so, in fact, your first question after I stop the video here is going to be to think about what happens in general for general P. And so I just wanted to give you some ideas to start you thinking here. I would encourage you to make this graph on your own and think about it as well as you're working this problem. The other thing to think about here is that all of these graphs, if you notice the order that they take on, to the right of x equals 1, you have 1 over x is on the top, and then the other functions go under it. So you have red, and then below the red is green, and then blue, and then purple. Well, it's just the opposite order if you go between 0 and 1 and look at what's happening there. And so you'll see kind of different behavior with convergence on the interval 1 to infinity as on the interval 0 to 1. So I'd like you to kind of think about that picture as you work the next couple questions, the last few questions that I've left for you to do on this worksheet back here. And so this is where we're thinking about families of functions. And so it turns out that these functions 1 over x to the p show up quite frequently and will be important as we study series coming up. So I'll just point out here, I'm asking you to think about varying p. And in the first question, I'm asking you to think about the integral from 1 to infinity. And in the second question, I'm asking you to think about the integral from 0 to 1. And lastly, I'm asking you to investigate another family of functions. And these are the functions where we have an exponential with a negative power here. And so I'd like you to go ahead and work through that. And I encourage you again to use Desmos to add a sketch. And in fact, let me just add that here. Include a sketch here in your notes, just to kind of remind you of the geometry of what's happening. Oops, I'm sorry. Include a sketch with, I meant to write several different values of A. And as we saw at the very beginning of this section from your preview activity, integrals of exponential functions show up quite a bit in probability distributions and elsewhere. So these integrals really you will bump into them quite a lot. Okay, and so that will conclude your notes that you'll send to me. In addition to that, after you've emailed me your notes, oops, I'm sorry, I have adjusted this in the actual assignment. So let me go ahead and change this here. So in addition, after you have done the last couple of exercises in the Your Turn bit above, go ahead and email those to me. Scan them in and email them to me, and then I'm going to ask that you do your gateway revisions and the first 5 problems in the back of the textbook, and send those to me as homework. Of course, all of this is at home, but this is sort of your follow-up questions so that you have some time to process and ask questions after you turn in your notes before you do these supplementary exercises. And so I'm going to ask that you turn these in by Monday. And we can say midnight Gambier time. And I just want to close by saying I am available if you have any questions and you want to discuss any of the material here or in these exercises. Please let me know. I'm happy to set up an appointment if you're not able to make my newly regularly scheduled drop-in video conference office hours. I'm happy to try to make some time to video conference with you, or we can work correspondence by email if that's better for you. The other thing I do want to point out to you is that the MSSC is going to be holding open hours. And so I'll be sending more information about that in a follow-up email. It will also be in your syllabus. So